Today we're going to talk about the life cycle of a star. Although a star is not technically alive, doesn't breathe, and it doesn't have organs and all that good stuff, it still follows a life cycle. It has a beginning and an end, so we call it a life cycle because of that. Their life cycle of the star is kind of similar at some points, and at some points it's different based on how large the star is. So we used to say there's two. We used to say there's the main sequence life cycle, and we say there's a massive life cycle. And we compare the size of the sun to all the stars, and that kind of tells us which way they're going to follow. If they're smaller than the sun, 1.5 times or smaller than the sun, we say it's a main sequence star. If it's 1.5 times larger than the sun, we call those a massive star. But all stars basically start in a nebula. A nebula is kind of like a star nursery. It's where all the baby stars come from. In the galaxies, there is collections of dust and gas, and those collections of dust and gas are called a nebula. And in that, basically what happens is gravity starts to pull in dust and gas, and it condenses and it starts to heat up and starts to create a star through fusion. So on your paper, you should put nebula, because this is where all stars begin, in a nebula. It's the birthplace of stars. As stars begin to heat up, they take on what we call a protostar. It's not quite yet a star, but it is beginning to get there. So we call it a proto, kind of like a prototype of a toy or a car. It's the beginning stages of it. It's what it's going to be when it's finished. So nuclear fission takes place. It basically takes all these hydrogen atoms from the surrounding gas and dust, and it starts to convert that into helium. So on the main sequence side, it's any star that's small to medium in size. It's usually 1.5 times the size of the sun and smaller. So we call it an average size star. As they continue on the average size or the main sequence life cycle, stars begin to change into a red giant. Basically, this is when their hydrogen supply starts to be burned out, and they start changing their helium into carbon, and this creates the star to collapse. Basically, it wants to preserve itself, so the temperature of the core starts to rise, and the outer surfaces of the star start to expand, and it cools off. And in space, it's opposite of what it is on Earth, but in space, red generally means that it is a cool temperature. It's not quite as hot. So the core is preserving, it's very hot, while the outer surface of the star is starting to cool off. It's basically puffed itself up into this giant stage, and it is trying to preserve itself. So here it is in the red giant stage, and it's going to continue. Those outer layers of that sun that star are going to continue to expand and puff itself out, and when it does, it kind of creates this planetary nebula. It's kind of its own version of a supernova. It's not quite to that extreme, but it does the same thing. It poofs out its outer layers and it preserves the core. We call it a planetary nebula. Last but not least, that star pretty much only has left its core after it loses all of its outer layers, and we call that a white dwarf. It's made up of pure carbon. It glows white hot. It's super, super hot, and it's basically will drift in space until it cools off. Once it cools off, we call it a black dwarf, and it's basically has nothing left of itself. It doesn't glow. It's done. It's basically going to drift around into space. The star is considered to be dead. It's considered to be at the end of its life cycle. And this star, although it's dead, is kind of neat. It will drift around in space until it bumps into other stars. And when it does, it will basically be turned back to dust, and then it can be brought back into the nebula and be returned into a new star later on. That's basically the life cycle of a main sequence star. About 95% of the stars that you see in the sky are considered to be on the main sequence stars life cycle. So it's pretty much all the stars follow this life cycle. However, there is another life cycle called the massive stars. These ones are kind of a little bit different. There are stars that are 1.5 times larger than the sun. They follow kind of the same life cycle. They start out in the nebula also, and basically, while they're in the nebula, they gather a lot more dust and gas. So although they're bigger, they're going to die a lot faster. So their lifetime is a lot shorter than a main sequence star. And this is due because gravity squeezes the core and creates greater pressures, resulting in a faster fusion rate. So again, it's considered a protostar, but this time it's a massive protostar. It's not quite to the star-like stage, but it is developing and it is becoming that large star. It's just like the main sequence, except for this time we call it a red supergiant. Again, it's preserving its core. It wants to keep that core together so that helium that it has made already is starting to become carbon, and it's going to turn it into iron, so it's a little cooler. Again, it poofs out its outer layers, trying to preserve all of its energy that it has left. So here it is following protostar to a supergiant. Once it has gotten to where it cannot preserve its core, it's basically run out of energy, it turns into a supernova. And a supernova are those really cool explosions that you see in space. And they're super, super bright. And in fact, sometimes they can be brighter than a galaxy, which is kind of neat. And this is basically where, depending on what's left of the star, it can kind of go one or two ways. So once a supernova has happened, it's going to continue to do one or two things. And the reason why supernovas and massive stars get to have two options of their ending is because they have so much more mass. They have a little bit of something left over when they're done. So they can become either a neutron star or a black hole. Now I, on the other hand, would like to be a black hole just because it sounds fun. I mean, black holes are one of those cool things that we're still studying out there in space, and we haven't been able to really get a good grasp on what all they're capable of, because first of all, you can't go in a black hole, can't send a camera on a string out there, it's not going to come back to us. I mean, can't put a flashlight in there and see what's happening. The only time you really know a black hole is there is when it starts to attack another star. When a star gets too close to its gravitational pull and it pulls that star in and it starts to take all of its energy, that's about the only time you can see a black hole. So they're kind of neat, and they're still studying them. But that's one of the options that a supernova can become, is a black hole. And that means you have to be extremely large. Have to be about 9 times larger than the sun. And the core will quickly collapse and become the black hole. If you're a lot smaller, if you're kind of like a little bit bigger than the sun, but not quite the total massive star that you could be, you get the option of becoming a neutron star. It's basically the core that's left over after the supernova has collapsed everything, and it's just composed of neutrons only. So again, this is how a massive life cycle of a star can end. It can become a black hole or a neutron star. All stars are classified by their size, their color, their temperature, and we have been classifying those stars for about the last, 30, 40, 50 years. And we've been collecting those stars on a graph called a HR diagram. This HR diagram has all the stars that we know of right now graphed on here. Most stars are about 95% of the stars are considered to be main sequence, or they're in the main sequence part of their life cycle. We have a few white dwarfs, we have some giants and some supergiants that we know of, but most stars are in this main sequence. Our sun, which happens to be a medium-sized star, is in its main sequence of its life cycle, and it happens to be the only star that is close to the Earth. It's about 1,000 times closer to the Earth than any other star that we know of. The sun happens to be about 5,000 Kelvin in temperature, and it also has about 1 luminosity. Luminosity is basically how bright or how dim a star appears. So since the sun is closest to us, we use it as kind of our basic marker. And so we say the sun has 1 lumen, or 1 lumosity. And so the sun will be right around in here on the HR diagram. As you move up in lumosity, you get a lot brighter than the sun. And then as you move down, these stars happen to be dimmer. The temperature works the same way. As you move from the right to the left, which is kind of backwards than we normally go, you start over here. These stars are a lot cooler, and as you move this way, these stars get a lot hotter. So here's a nice little website I found to kind of explain to you how it works. So here's, again, the HR diagram. Notice stars that are at the top on the left are hot and bright if you're at the top, and on the right, you're bright and cool. And here's the sun. They've marked it for you. It's right about, it's a little more than 5,000. And here's the luminosity is 1. So if you're on the bottom, down here on the left, you're going to be hot and dim. And if you're on the right, you're going to be cool and dim. Remember, in space, if you're hot, you're considered to be kind of a blue and white color. If you're in cool, you're going to be kind of in that red, orange, yellow stage. It's opposite. So here it is again. They've marked the sun for you on the main sequence. These up here would be your giants, supergiants, and then these down here would be your dwarf stars. There's another picture of it. Here's one that's kind of neat that has it all kind of color-coded for you. There's all your supergiants. It has them color-coded for you. It has all your blue ones over here, and then all your red ones over here. Remember, these are cooler. These are much hotter. And there's another one. They have these neat little lines on here. We don't need to know about that right now. But this is how we are going to be classifying stars. Tomorrow we're going to be classifying our own set of stars, and you're going to be responsible for figuring out where on an HR diagram they might go based on their color, their temperature, or maybe their size, or their lumosity.